Good morning, students. We are continuing with the bonding lesson 3. In lesson 2, we looked at the concept of hybridization. To understand the concept, we gave an example of carbon. Carbon has got an atomic number 6, and the electron configuration is 1s2, 2s2, 2p2. If we put the electrons in their appropriate orbitals, we have 2 electrons in the 2s orbital, then one electron in the 2p orbitals, leaving one empty 2p orbital. When we look at that electronic configuration, it means carbon is a bivalent element, but that is not the case. Because of excitation, one electron from the 2s orbital is promoted to the empty 2p orbital, giving rise to 4 unshared electrons, which accounts for the bonding characteristic or capacity of carbon in its compounds. That one has led us to the concept of hybridization. Hybridization is the mixing up of different atomic orbitals of the same atom, having approximately equal energy to form new equivalent orbitals known as hybrid orbitals. We looked at examples of hybridization where we gave sp hybridization. An example was beryllium fluoride. That one gave a linear molecule with an angle of 180. Another example was sp2 hybridization. That one, an example was boron fluoride. That one gave an example of 120, and so many other hybridization. Today, we are going to look at theories, and the first theory we are going to begin with is the valence shell electron pair repulsion theory. This theory predicts molecular shapes and bond angles more accurately. It states that the lone pair and shared pair arrange themselves around the central atom in space as far apart as possible to minimize the electrostatic force of repulsion. Always, a system with the minimum repulsive force is said to be stable. The important points to note in this theory is that the first point is that a lone pair occupies more space than the bond pair because it is attracted by only one nucleus, while the bond pair is attracted by both the nuclei. Therefore, the order of decreasing repulsion is lone pair has got a greater repulsion than bond pair, lone pair, also than bond pair. An example is the water molecule, methane molecule, ammonia, and the water molecule. If we look at their arrangement, they are all sp3 hybridized. And when we look at the structure, they all have a tetrahedral structure. And the bond pair, methane is having 1, 2, 3, 4 bond pair, while ammonia is having 1, 2, 3 bond pair, and water is having 1, 2 bond pair. When we look at the lone pair, methane is having no lone pair, ammonia is having 1, and water is having 2. The principle said that lone pair occupies more space than the bonded pair. So because of this, the lone pair push the bonded electrons far away from the lone pair, thereby bringing them close, hence decreasing the bond angle. That's why the bond angle for water is less than that of methane. Another point is electronegativity. If we consider a molecule of AB type with increasing electronegativity of the atom B, an example is phosphorus iodide, boron bromide, and phosphorus chloride. Chlorine is more electronegative than bromine, and in turn is more electronegative than iodide. So because of the electronegativity of chlorine, the bonded electron pair position moves further from the phosphorus, thereby decreasing the force of repulsion exerted by the bonded electrons from the electrons of phosphorus. And as a result, the bond angle decreases. That's why phosphorus chloride is having a less or a smaller bond angle compared to phosphorus iodide because of differences in electronegativity of the attached atom. That explanation is shown in this slide. You can pause and read more. Another point, the repulsion between the electron pair in the field shell are larger than the repulsion between the electron pair in the incompletely filled shell. An example we can give here is water molecule and the hydrogen sulfide. The bond angle for hydrogen sulfide is less than that of the water molecule. The reason being, in the water molecule, oxygen has filled shell, and on the other hand, due to the empty d orbital in sulfur, there is expansion. What do we mean? Oxygen is the central atom. The atomic number is 8. Electron configuration is 1s, 2s2, and 2p4. When we come to sulfur, the atomic number is 16. Electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p4, and 3d0. There is no electrons in the d orbital. So because of the empty d orbitals in sulfur, expansion takes place, and hence there is less repulsion. An assignment I can leave you with: explain why the bond angle of the following molecules having the same empirical formula decreases. Another theory is the valence bond theory. You can call it BVT. This theory gave a theoretical treatment to the explanation of the formation of a covalent bond and the energy changes taking place. The main points of this theory are: it deals with the electronic configuration of the element. Another point is, it says that it is the number of unpaired electrons present in the valence shell of the atom that take part in bonding. The unpaired electrons and the paired electrons are unpaired if they are to participate in a bonding. And the energy released in the formation of the bond provides the energy required to unpair such electrons. Another point with this theory, the covalent bond is formed by overlapping of appropriate orbitals. And this process, pairing electron spin, take place. Another point with this theory is that during overlapping of the orbitals, the unpaired electrons are paired to form a covalent bond. Some defects of this theory. This theory failed to explain the paramagnetic behavior of oxygen and other molecules. To remind you a bit what paramagnetic is the weak attraction between an element and a magnetic field. Diamagnetic is the weak repulsion between an element and a magnetic field due to the presence of paired electrons. While ferromagnetic is a strong attraction between an element and a magnetic field. Mainly transitional elements are ferromagnetic. Therefore, this theory failed to explain the paramagnetic behavior of oxygen and other molecules. Also, the VBT theory does not offer any explanation to the formation of a coordinate bond. In this coordinate bond, both bonded electrons are provided by only one atom. It also fails to explain the bonding in the diboron molecule. The diboron molecule is an electron deficient molecule, and also fails to explain the bonding in other molecules. It does not offer any explanation about the color of the compounds. Remember, the transitional elements are colored. The VBT does not offer any explanation of any colored compound. Next time, we are going to look at the molecular orbital theory, read about the theory so that we can get a lively interaction.